There we are. Now I'm recording. So that first part of the lecture, actually, I already forgot to record it. And I will be posting these at some point on the website. Now, just a word of caution. Don't rely on that. Don't miss classes or miss this scheduled time just because things are going to be recorded. Because like I just demonstrated, I may forget to hit record at some point of the lecture, and I'm not going to go back and do it again. So I am going to run this class synchronously. And so the recording part that I will post later is really just more of a convenience for review, or in case you did miss something, if there was an emergency, things like that. Then hopefully the recording is there on the website for you. Okay. Any questions thus far? Feel free to unmute yourself and yell something out if you ever want me to pause or to answer a question. Don't feel like you got to stay on mute the entire class. I know there's chat going on. There is a lot kind of going on for me, so I don't always see chat. I am periodically trying to glance at chat. But if you have a question, please just unmute yourself and say, hey, stop. What's this about? What's that about? So don't feel you have to stay quiet. Okay. Let's see. So that kind of takes care of this first page. I already talked about the online format. I'll briefly go over kind of our objectives here. We are introducing electrical circuits. We're going to be working with different components, different circuit elements, electrical devices, how to put these together. Like I did say, we are learning a lot of basics, so I know it can be a little tedious, and a lot of the times it's like, well, what's the application of this circuit? There is no practical application of the circuit other than to serve as a teaching aid to learn more advanced circuits that actually can do useful functions for us. So I do apologize if at some times or actually a lot of the times, if the circuits we're looking at are kind of like, why would I ever do this at work? We're building up a set of tools here and learning so that we can apply them to much more practical circuits, and the bulk of those do pop up in 311. So try to keep your eye on the prize, right? We're just going to be going through the motions for the sake of being able to do more useful advanced things later. Okay, we're definitely going to be going over schematics, how to draw these circuits, modeling tools, how to simulate the circuit and verify that things are going to work before we hook them up. Out of curiosity, just so I get a little interaction at this point, has anyone taken Physics 152? I got one person that kind of sounded like a yes. But I heard 3 people. You're taking it right now. Okay, so about 4 people taken 152 or have taken it. Okay, I'm very sorry for you guys. If you're taking 152 or you've already taken it, there's going to be a little bit of repeat in here. However, what I will say is I am not a physicist. So in 152, you're working with electricity and magnetism. And so you are going to learn some of those basic fundamental circuit stuff. But then at the same time, you're going to also calculate the magnetic field around a wire and things like that we will never do in this class. So there is some overlap over there. I had nightmares with the class. I'm reading chat right now. I will agree with you. I had nightmares taking 152 as well. So this class is a lot more practical, introductory to electronics, and not so much how to calculate magnetic fields around things. So usually that works out better for most people. And then there's one person that's like, but I want to calculate the magnetic field around a wire. Okay. So some of the things we're going to be covering, your basics, Ohm's law, series, parallel circuits. We're going to cover resistors, capacitors, inductors. If all of this sounds like gibberish, don't worry about it because we're going to learn about it later. We're going to go over some measuring tools, some instruments. We're going to hopefully by the end of the semester get into oscilloscopes and looking at waveforms live. And also some of the more practical stuff, breadboarding and soldering and things like that. I will speak about the lab materials in a minute. First, let me mention the book you're going to want to get. The book is Grob's Basic Electronics. It's written in the syllabus. This is actually a pretty decent book for an introductory and even an advanced 311 circuits course. So this book will be good for 211 and 311. It's one of those books that's, a lot of older electrical engineers still have an older copy of this book on their shelf, and they make use of it as reference even after they've graduated and, worked in the field for 20 years. So it's not a bad book, and it's very practical based. There's very little to no calculus. So if you're looking for calculus, there's a math department. In this class, I won't be doing any calculus for these circuits. You don't need it. As far as software goes, I know it says over here Multisim 11.0. Don't worry about this one. We're going to be only using LT Spice. Now, LT Spice is free and it's from Linear Technologies. You can download it from my website. So if you go back to the 211 website, under the tools section, I have an LT Spice download. This is a zip file, and inside of it is not just LT Spice, but I've also added a lot of components to it that we will use in this class and also in 311. So you can download the one from the website Linear Technologies if you just did a Google search for LT Spice. However, you're going to be missing some of the components that we're going to want access to. So I've added a lot of stuff specifically for me and for things that help students later in like 490A, 490B, and 311 and those later classes. So download the zip file from here. Now, there is a Mac version. Now, I should say my copy is a Windows version. There is a Mac version that's available on the Linear Technologies website. They're the manufacturers. They're the ones that made this program. The problem with the Mac version is that it's got this very awkward interface that's missing a bunch of things. And so I've had students try to use the Mac version in the past, and they always end up hitting a wall at some point in the class or even on the first day of class trying to use the tool. Now, most of the software that we use falls under this umbrella category of EDA tools. I'll go ahead and write this up. EDA tool stands for Electronic Design Aid. Now, all of the tools that we use in the engineering program, LT Spice, for making schematics and eventually making circuit boards. In fact, I'm going to teach, I'll have a tutorial later on for how we can get started making our own printed circuit boards. So when you're talking about, constructing a useful circuit, I'm actually looking around for an example right now. We have breadboards that we can go ahead and place components into, and this is a nice, really easy, convenient way to put components into or onto and construct our circuits that way. But if you want to make something a little more hardy, something that's going to go into a product, you do want to make a circuit board. And so I will have a tutorial series on how to construct our own circuit boards, which is kind of nice. And all of this software falls under this umbrella category of electronic design aid. If you've taken 201 or you are taking 201, then you're using Xilinx, and Xilinx is an EDA tool. So one of the things I do want to emphasize, when we're going out and we're getting that internship or we're, in an interview situation, you want to make sure you're always as precise as possible with the terminology you're using. Nothing looks worse in an interview than incorrectly throwing terms around or not using the correct terms for what it is you're talking about. For the sake of your future career, I want everyone to really kind of get in that habit of learning the correct terminology for things so that we really know what we're talking about, because that's going to make the difference for getting that job on an interview. Whether you're like, yes, I've used that EDA tool, or yes, I've used LT Spice to model my circuit. You want to go ahead and use the correct terms. So we'll be using LT Spice primarily. Now we kind of get into this gray area that I don't have a good answer for yet, which is the lab supplies. My goal is for everyone to use to actually construct these circuits at home. However, the department and me, the department chair, I should say, and myself have been collaborating since the beginning of summer on getting these lab kits out to everyone. And I'm still waiting for an answer of the school paying for this. Now, if you're interested in what it is that I plan on using, it's called the MyDAC. MyDAC is by National Instruments. And the website should come up eventually. Here it is. Okay, it's this little box. It's a USB-based test and measurement equipment. So it has an oscilloscope, it has a multimeter, it has a power supply, it has a function generator, all of these things that we can use in the lab to actually build up our circuits and test them out. So hopefully I'm going to get an answer within a week of us getting this. And so probably about the midway point of the 211 class, we're going to switch over from doing primarily modeling of our circuits and simulating them in software. We're going to transition over to working with them on our breadboards, and we'll be constructing them this way. And so I'll have more information on components, anything you would have to buy. One thing I will say is I'm very conscientious about how much money students feel they have to spend for a class. Now, as far as materials, buy the book, download the book. I don't care. However you get a copy of the book, just get the book. But I know I try to keep materials and costs down in the $50 range. So if we do have to purchase anything, I will make sure to keep that cost as low as possible. Okay, any questions thus far?
Are webcams like required?
That's a good question. Can I require someone to have a webcam? I don't think I can. So I would love to have a webcam on everyone during the test taking process. The problem becomes, if even one student tells me my web camera broke right before the exam, what am I going to do? I can't do anything about that. So the quick answer to your question is no. I can't require a web camera, and I don't feel right doing so because invariably at least one person is going to not have one for some reason, and then that's an unfair advantage during an exam or whatnot. So no web cameras are required. I will mention a little bit about the exam right now. I mean, I'll go over the exams process a lot more in detail as we get closer to it. I always do an exam review session before the exam, and the exams will be on Beachboard. The exams will use that Beachboard quiz function for the exam. It'll be timed. Everyone will start the exam at the same time and finish at the same time. I create question pools, and then they're randomly selected for every person. So everyone does get essentially a different randomized exam. I don't just have 10 questions and they randomly change order. For each area that I'm interested in on the exam, there's usually like 3 or 4 versions of that question, and so they get randomized for everyone. So that's kind of how I'll do the exam process. But yeah, good question on the web camera. Any other questions? Okay, so let me go over the grading plan over here. So as far as things that we have, quizzes, I'll only be counting the 5 highest ones, or if we had like 4 quizzes, I'll just drop 1 or 2 of them. I will always end up dropping a quiz. I do my best to announce beforehand when there's a quiz. Wait a second. Because it's on Beachboard, yeah, it'll have to be announced beforehand. We will have 2 midterms. So I'll have one midterm approximately around week 5, and then I'll have another midterm about 3 weeks before the semester is over, and then we'll have a final exam. The 2 midterms are worth 20% each. The final exam is worth 25%. And the labs and homework all together is under one category that's worth 25%. As far as late work, please, if you're late on something, get it in. But I will be taking 5% off per day. So we meet on Tuesdays and Thursdays. So if it's due on Tuesday and you turn it in on Wednesday, it loses 5%. If you turn it in on Thursday, then you lose 10%. So it is per day. So be careful if something is due on Thursday and you get it in the following Tuesday. That's Thursday, Friday, Saturday, Sunday, Monday, and then you turn it in on Tuesday. So that would be 5 days late. As far as the grading goes, I enter all of these in on Beachboard. So Beachboard is always going to have the graded materials on the grade book over there, so you can see that at any time. I will be entering in the scores as is. but I will be curving the class. Now I curve only once. So once all grades are entered into Beachboard, they're just going to be entered in as is. And then at the very end of the semester, I look at the top 3 or 4 people in the class. I average their grade together, and then I do a linear shift of all the grades upward. So that's kind of how I do my curving. Now, the lower you go in the grades, the more help I find people at the bottom need. So I may do a linear adjustment up here, but then people at the bottom get boosted a little more. But what I never do is the order never changes, so nobody will ever get curved more than somebody else. That would be silly. So that's kind of how I do my grading, but just so you know, you aren't going to see curved grades entered into Beachboard. You're just going to see the raw value, and then at the very end of the semester, everyone gets curved and bumped up. Now, what does that look like is usually about 5 to 10%. So if you're at like an 85% or an 88% in the class, usually those just get bumped up into the A category. But it does depend kind of on the overall performance of the class, what that curve actually looks like. So I'll give I'll give an idea of what that looks like after the first exam, okay? Are there any questions in regards to the grading? Does that make sense? I got one question. Are you going to be the instructor for lab, or is it someone else? I will be your lab instructor. Which works out well for me. When I have, a lab instructor, someone else, oftentimes it's a little harder to tie in the material between the lecture and the lab. So me being a control freak, I like having the lab myself, because I get to re-emphasize and reinforce, what I feel is important from lecture. Okay. I do apologize. We're going to be going over time today and going into the lab time. I will have a demonstration in the lab. I'll let everyone take a break here in a little bit once we're done with the syllabus. As far as attendance, I am going to be recording attendance, maybe every day or maybe every other day, but I'm going to be looking at attendance periodically. I normally don't, but given this online awkward situation, I'm very worried and concerned that, some people are just going to, fall off the bandwagon or stay asleep by 9:30 and whatnot. So just to keep all of us on our game a little more, I'll be checking attendance, okay? Cheating and plagiarism, please don't cheat on exams. Don't have a Discord channel while the exam is going on and everyone else is talking about the exam. That's not fair to people who are not on the in crowd, who don't have access to that Discord channel. I do my best to try and make these exams as fair as possible. Hence the randomized questions, hence the question pools. And also there's always a bit of a time constraint with the exam. Yeah, please don't cheat. My biggest concern is the exams, and then second are the labs. So just be honest, do your own work. Where I'll tell you where it stands out for labs is where you take like a screenshot of your work and then somebody else is like, oh, I didn't do the lab, and then they share the screenshot and then I get two identical screenshots. I tend to catch those, so please just do your own lab work. Don't rob yourself of your chance to learn here. On top of that, once you get to 311, all of this 211 material, you really have to know like the back of your hand. You don't have time to second guess yourself. So as far as being a good engineer in the long run, you really do need to learn this stuff and know it intrinsically. For me personally, I'll tell you from experience, when I was a student, we had one electronics class, and I did okay in it, but, you know, I passed. But I didn't know it, and I struggled with electronics for my entire student career. And then I graduated and I started working at a few different companies. And I noticed how lacking I was in the area of electronics. I couldn't keep up with electrical engineers. I had to then go back into my own remediation, and I started learning these things, you know, on my own and with the help of fellow engineers that I worked with at my workplace. And slowly, I painfully built up that electronics skill. So I know how easy it is to sort of dismiss electronics in this program because, you know, you're working in 201, you're doing software classes, you're doing all of this other stuff. And then at the same time, you have this little nagging electronics in the background. And you're kind of like, well, I can kind of hook up an LED and I can make it blink and whatnot, but I don't know what's going on. So I beg everyone to stay on top of this electronics skill. Get into it. There is so much out there in terms of YouTube and other people that make awesome and amazing content in the area of electronics. It's a never-ending field that I am constantly learning stuff all the time. So at this point, I absolutely love the analog area of interfacing to computing systems, and that's one of the things I sell myself on when I apply to a job. There's a lot of good software engineers out there. There's not a lot of people that are good with computing systems and are very good with electronics. So this is one of those skills and one of those areas you beef yourself up on, and you're going to have no problem landing awesome jobs later. Okay, there is a tentative schedule. I'll kind of be loosely following this, but this is just kind of an idea of the topics that you're going to encounter and kind of the order that we're going to progress through this. Perfect question right now. Does anyone need to add the class? Type it in chat if you need to add the class. I know there were like 3 or 4 people. I got 2 I do's. Sorry, I wanted to check my emails just in case anyone else just emailed me wanting to get into the class. Okay, if you need to add this class, here's what you're going to do. Okay, send me an email first and foremost. I'll go ahead and write that over here. Email me. And when you email me, and this goes for all emails and all correspondence with me, I have like 160 students, and it's hard to keep track of all of these emails once we get into the thick of the semester. In the subject, make sure you put CECS 211 and then your name. That way, right off the bat, when I see the subject of the email, I know that it's my 211 class. It's a student from here. Okay, so you're going to go ahead and email me. In that email, you're going to do name, student ID, and a picture of proof of the prerequisites with C or better. Okay, so the prerequisite for this class is Math 122 with a C or better. I don't care about any of the other classes. You can black them out if you want, but all I need to see is a line that has Math 122 or equivalent and a C or better in the grade. Once I have the email with your name, student ID, and the proof of the prerequisite, I will then assemble an add list. I will forward that to my department chair, and then they'll give you permission to add the class. Okay? You will still need to add the class through my CSULB, just like you added any other class, but there will be a permission slip that gets added. And so that's how we can get you into the class. Now, if there's only 2 people, I am hopeful that there won't be any problem. But get me that email, and please get that to me by today. So once this class is over, don't leave this till the last minute, because I have to submit these, and then if somebody comes later and wants to add, I would have to, I don't know, create another add slip, and then it gets messy as far as the department. So to keep things streamlined and to keep things working smoothly, get it to me today. For the prerequisite, you can just go to my CLCLB, look at your unofficial transcript, and just take a screenshot, black out everything else, and just show me that one line that says C or better. Okay? Okay, so any questions on adding? Okay, perfect. Accommodations, of course. I've seen a couple of emails. Remind me if there's anything that I have to do as far as submitting back to the BMAC office or anything like that. And I know there's usually like time and a half on the exams and things like that. So just let me know, and we are happy to do whatever we need to. I'm hoping that between the recording and posting and the video, as long as I have enough media going out there, people can review things, slow it down, whatever it is to get you going. You can go ahead and read this section. This is a new section they asked for on our syllabus from the school. Food and housing assistance. Long Beach, Cal State Long Beach is a small city. We have programs to help with anything and everything. So any problem that you're having, there is a department on campus that can help out with that. So please, and if you have any issues with anything, send me an email and I will do my best to find out where there is some support on campus to help out with whatever it is. Okay, so that takes care of the syllabus. We are at 10:22 and this class goes till 11:45. Okay, let me talk. I know I'm talking a lot. Let me go ahead and just briefly go over my past a little bit so you know what you're paying your money for here at Cal State. Now, I got my bachelor's degree from Long Beach here at Cal State. I then got my master's here from Cal State Long Beach. I grew up like maybe 5 minutes from Cal State Long Beach, and then I bought a house over off of Palo Verde and Los Coyotes, again about 5 minutes from Cal State Long Beach. I just can't leave this place. I like it here. I have a friend that likes to joke, and he says, when people move to Long Beach, they think to themselves, my grandchildren are going to like it here. It's a hard place for me to leave and get out of, so I love this community. Now that being said, I got my bachelor's degree in computer engineering. I then got my master's degree in computer science with an option in computer engineering. Also, while I was working on my undergrad, I worked at the first company I ever started at. That was Dice Electronics. And Dice Electronics made these little products. Now, in 2001, 2002, finding smartphone integration to your car was a thing that did not exist yet. That didn't come standard. So we made aftermarket units that would interface, at this time, your iPods and flash drives. And eventually we added Bluetooth capability to it. And it would all seamlessly work in your car. And if you had a high-end car like a BMW that had steering wheel controls at the time, that would control your iPod. So we would actually reverse engineer the car communication in order to hijack the controls of your head unit, your stereo, or any controls that the car had. We would then interface that to your iPod and then mix the audio in with your car. It was actually a pretty cool company and a really awesome opportunity when I started working there, because I was just a young person that didn't really know very much. And so they were happy to let me learn. They were a startup company. They weren't paying very much at all. In fact, my first couple of months, I didn't get paid at all. But the experience was invaluable, and that's what let me get all of my future jobs. So I am actually indebted to this little startup company, and it grew pretty quickly. From this little startup in Signal Hill, we were then making units for Honda. So if you went to Honda and you purchased one of their vehicles and you wanted the Sirius package for the satellite radio, they actually sold you our unit that we made for them. We also made units specifically for the company Sirius Satellites. So we made some units for them. They put their label on it. We also, does anybody own a Subaru? Anyone here with a Subaru? Say it in chat. Anybody's mom have a Subaru? Anyone's dad have a Subaru? Their next door neighbor has a Subaru? My dad. Perfect. Okay, so your dad actually has one of my products in their car. If you go and open that center console and you take that thing apart, underneath it is actually my design. Being able to say that is really cool. The fact that I made something and 10 years after the fact it's still being sold is awesome. Yeah, that was the first company I worked at. Later on, I started working at a company called NDT Systems. NDT stands for Non-Destructive Testing. Specifically, we made ultrasonic units for inspection. So we made this. I did a lot of the code and programming and some of the hardware on there. I learned a lot at this company. We also did these flaw inspection units. So when you think of like an airplane goes from sea level all the way up to 22,000 feet. And over there you have much colder and less air pressure, and so the wings and all the materials and the fuselage, all of those composites and aluminums and titanium, they all get stressed back and forth with repeated landings and takeoffs. And so you want to be able to periodically inspect them for flaws. So we would make these handheld inspection units. And that was a really cool company to work for too, because again, a computing system, it's interfacing with ultrasonic sensors, and then it's doing quite advanced analysis on the data that you get back from those sound waves, and you can find flaws and stresses and fractures without actually having to cut the part open and take a look physically inside. So it's a nice process for inspection. So I worked making those for a while. I then worked at an electric bus company where I designed if you think of like a power supply, a switching power supply for your computer has to take AC in and then turn that into all the different voltages. I essentially designed the same type of thing for these buses. Now, these electric buses run off of 600 volts at 300 amps. We're going to learn volts and amps in a bit. But that being said, it's a lot of power, and it was actually the most power I'd ever worked with before. So that was kind of one of the neat, interesting things about working at this company was I learned a lot about battery technologies, different types of electric buses. We had buses that ran off of natural gas, like natural gas turbine buses. We had fast charge systems that could charge in 5 minutes. We had other slow charge systems that would charge overnight. We did if you've ever seen this trolley hanging around San Diego, we actually made these. We made the entire bus in-house. We had a warehouse with full fabrication and metal shop and welders, and they would actually make these things. And we even had a giant paint booth to do all the painting. And I did a lot of the electronic systems, a lot of the software to control the power from the batteries to the motors and back and forth. So that was another cool company. And now I teach here. Okay. What are we at? 10:30. Another thing, as far as kind of myself on the side, hobbies, I absolutely love the outdoors. I do a lot of canyoneering. That's this kind of interesting niche sport where you go through these canyons. Wait, I had some other pictures. Here we go. You descend waterfalls on ropes. This is my wife over here. This is me. Here's an awesome picture that I took of my wife coming down in Zion. This is a canyon called Engelstad Hollow. And you can see her. It's a little dark, but you can see this is actually a 300-foot rappel. So we do all the technical throwing the ropes, setting up the anchors, doing all the rigging and all of the, life crucial technical rope aspect of descending these canyons. I try to go almost every other weekend. I'm somewhere else doing this. I do have a page on my website that I just have like outdoor adventure stuff. If you're ever interested, feel free to watch any of these videos. I mean, that's why they're posted there. You can see in Zion a couple of the drop-ins. There's also a lot of local canyons with, good 150-foot waterfalls like this one. Here, I'll play this video real quick. So you can't really hear the audio. but there is a good-sized waterfall coming over. And this one's about 150, so I get very small at the end of that video. Okay, I also do a lot of backpacking, I like the Grand Canyon a lot, and a lot of our local mountains. So if anyone's interested in hiking or any type of outdoor stuff, let me know. Okay, oh, sorry, what's up?
You're all good. I went backpacking a few weeks ago and I got stuck on the beach for 6 miles.
Where at?
It was in Virginia. It was I don't remember.
That must have been humid.
It was terrible. I thought I was gonna die.
Yeah, I don't know if I would want to backpack over in Virginia. It's pretty humid right now, and on Sunday I was out taking some beginners through a canyon over in near Mount Wilson. It's actually on Mount Disappointment, which is right next to Mount Wilson, and behind that is a really cool canyon with like 9 rappels. And me and my wife were taking out some beginner friends, and it was so humid, and the gnats, there were just little flies like a cloud around my face for like a full hour and a half on the approach. Fortunately, once we dropped into the canyon and we got into the technical portion, the gnats kind of let up, but I was kind of surprised. I've never seen that many little insects flying around my head for so long. And that's not true. One time I got chased by mosquitoes for like 4 miles, and that really sucked. But that was years ago, and I'd already forgotten about that. And then the gnats. Also do a little bit of off-roading and some other stuff. My other big hobby is astronomy. So I love doing telescope astronomy outreach. We used to go out to Seal Beach, and we would have an astronomy night with a few other amateurs in the area, and anyone walking by can go and look through our telescopes, and we'd show them Saturn and deep space objects and other things. So yeah, if those events ever start back up, because we're just kind of still in this awkward COVID phase, I will let everyone know. I can also do some live streaming from my telescope, which I may try at some point in the future. I can send out an email to everyone and let you know, click on the link and maybe see, the moon, Saturn, Jupiter. They're all looking really cool right now, as well as a few deep space objects, globular clusters, and some nebulae and things like that. Okay, so I am done talking about me. Okay, so any question before we go for a break? Okay, let's go ahead and let's take a 10-minute break, and let's meet back at 10:45. Okay, I will officially start the lab section at 10:45. And I do have a demonstration to get to. Okay. After that, we'll go ahead and depart ways, and then I'll see you again on Thursday. Okay. So I still need to take roll. I will do that at the beginning of lab in 10 minutes. All right. Cheers for now, and I'll be back here. snacked on something earlier. And everyone can hear me right now, right? Okay, so I'm going to start out my story about 2,500 years ago with this Greek philosopher by the name of Democritus. Now, Democritus sat there like a good Greek philosopher, pondering the nature of existence and thinking to himself, what if I took this rock? And what if I took this rock, I broke it in half, and then took one of those pieces, and then I took that one half and I broke that in half again, and then I get another two pieces, and then I take that and I keep on doing this. I keep going down this whole line. And he thought to himself, there must be a point at which I can no longer divide this. And he called that the atom. Atom comes from the Greek word atomos, which means that which cannot be further divided. Okay, now fast forward 2,500 years later, turns out he was not far from the truth. Now we know there is more underlying structure in the atom. There are quarks, and there is quantum field theory and quantum field dynamics and all of this stuff. But it is still relevant and accurate to talk about atoms. And so the first useful model of the atom was created by Niels Bohr in 1913. Now, you will know this. This is the atom that we're all familiar with from high school. Okay, hopefully everyone can see this just fine. I'm going to try and save some time by not redrawing this. I will say for future lectures, I always handwrite everything out so that everyone has enough time to be able to copy their notes. So I do suggest that the best way to take this class is to have this screen full size and then take your own notes on the side, have your book there on the side as well, and create a good learning environment for yourself. Trying to view these lectures and learn by just watching it on a smartphone at some coffee shop is not the ideal way to do it. You will have trouble seeing the lecture and following along. So please do yourself a favor, create a nice quiet situation, or at least the best that you can, and take your notes on the side, because doing the hand motion, watching the lecture, maybe even looking at the lecture again later as it's recorded and posted, all of this stuff is going to contribute to you learning. Okay, so what do we have in this atom? Well, we have something in the center. This whole area in the center is referred to as the nucleus. In this nucleus, we have a proton. Now, a proton is denoted with a positive sign to refer to its charge. So everything has the ability to have a charge associated with it, either a positive charge or a negative charge. Now, along with this proton in the center of the atom, the nucleus, we also have a neutron. And the neutron has no charge, so we're just going to call it neutral, or that's where it gets its name, neutron. So we have a positive charge and we have a neutral charge, and they're all hanging out in the center. And then in orbit around this nucleus, we then get these electrons. And these electrons, I denote them with a minus sign for a negative charge. Okay, so positive charge in the center, negative charge on the outside orbiting. Now, if we know a couple of things about any given atom, we can then know more things about it. So the first thing we would like to know to describe the organization, and in fact, I'm going to write this one out. The organization in an atom, and I'll go ahead and call this rule number 1, is that the number of electrons equals the number of protons. So if we got one proton in the center, we should have one electron in orbit around it. Okay, so I'll go ahead and say number of electrons and oftentimes I will denote an electron with an E raised to the minus, since it's got a negative charge, equals the number of protons. Okay, so that's kind of our first rule. Now, since we're dealing with electronics, I think it's a good idea to actually start with something that is good at conducting electricity, and we will talk about what makes a good conductor in a minute. But let's just go with copper. We all know that copper is really good at conducting electricity. That's why we use it for wires. Now, for copper, the only bit of information we're going to need to start this off is the number of protons. Well, for this, you go ahead and you look at the periodic table of elements. It will tell you how many protons something has. Copper has 29 protons. So, I'll go ahead and ask it, how many electrons should we have? Put 29 in chat.
29.
Perfect, 29 electrons. By rule number 1. Okay, so now to save time in drawing 29 little circles, what I'm going to do is put one circle in the center, and I'm going to write the number 29, okay, for 29 protons. Now, the electrons are not just going to willy-nilly spin around the nucleus of this atom. They're actually going to align themselves. They're going to organize themselves into orbits that we refer to as shells. Okay, now I've drawn 4 shells, but you could have 1 shell, you could have 2 shells, you could have 3 shells. The number of electrons is going to determine how they organize themselves into these shells. And for the sake of convenience, I'm going to go ahead and label these shells from the inside outward as shell number 1, shell number 2, shell number 3, etc. Okay, so we'll go from the inside out. Now, we need to figure out how many electrons. Do we have 29 electrons in shell number 1, or do we have 5 electrons in shell number 1? How do we figure that out? Well, we're going to go ahead and use another rule that I'm going to give you, which I call rule number 2. The max number of E's, the max number of electrons, in shell number n equals 2 to the n raised to the 2. Okay, so a shell cannot hold an infinite number of electrons. There's only so many that you can stuff into this first orbit. Similarly, there's only so many electrons that you can stuff in shell number 2, and etc. So this little formula over here, 2n to the 2, actually tells us how many electrons we can put into that first orbit. Now, the easiest way to do this is for me to set up a little table. In my first column, I'll put the shell number. We have 4 shells. So 1, 2, 3, and 4. I know, it's a little cut off. Okay, and now in the next column, I'm going to put the max number of electrons that that shell can hold. So for that first shell, we use that equation, and since it's shell number 1, the max I forgot to write the word max over here. Okay, so max number of E's in shell is given by 2 to the 1 raised to the 2. In other words, shell number 1 can only hold 2 electrons. Shell number 2, 2 times 2 raised to the 2, which equals 8 max. Okay, so I can only put 8 electrons into shell number 2. Keep on following with this. You'll find that shell number 3, or 2 times 3 raised to the 2, equals 18 max. And shell number 4 can do 2 times 4 raised to the 2, or 32 max. Okay? So that's the max number that they can hold. Now what we're going to do is we're going to work from the inside out. Now we're going to look at it specifically for copper. Okay, so number of electrons in shell for copper. Well, we have how many electrons that we have to fit into this? We have 29. So if I can only put 2 into shell number 1, then shell number 1 is going to have 2 electrons in it. So for shell number 1, I can go ahead and draw that. 2 electrons. Now, how many remaining electrons do we have to stuff into the remaining shells, right? Well, just take 29, subtract 2 from it. So I'll set up another column over here. And I wrote remaining over here. Sorry about that. Okay, so 29 minus 2 gives us 27 remaining. Now, from those 27, how many can I put into shell number 2? Well, I can stuff 8 of them. So now I get 8 electrons in shell number 2. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so shell number 2 is going to have 8 electrons in it. Well, how many electrons do we have remaining from that 27 if we've now taken 8 of those electrons and put them into shell number 2? We have 19. Okay, of those 19 electrons, how many can we stuff into shell number 3? Well, we can shove a max of 18. So I can put 18 of those electrons into shell number 3. So let me go ahead and draw that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay, so 18 of those electrons go into shell number 3. Now, obviously, I haven't drawn this perfectly. They're going to spread out. They're all negative charge, so they'll all spread out as much as they can. Okay, but from those 19, we put 18 of them into shell number 3. So how many do we have remaining? 19 minus 18, which gives us 1. Okay, now how many electrons can we stuff into shell number 4? Well, we could put a max of 32, but we don't have 32 left. We have 1 left. So this 1 electron is going to hang out all by its lonesome here in this outermost shell. So what does that look like? This lonely electron out there, all orbiting the outermost shell by itself. Now, we have a name for this lonely electron. We have a name for all of the electrons that hang out in the outermost shell. Any electron that is in the outermost shell is referred to as a valence electron. Okay, so in this case, we have 1 valence electron. If instead we had 2 electrons hanging out in the outermost shell, we would say we have 2 valence electrons. But for the case of copper, we only have 1 valence electron. Now, this actually ends up being very useful for us, because if we know the number of valence electrons, we know how conductive a material is, or how easy it is for electricity to move through this material. Or in other words, the fewer number of valence electrons we have, the easier it is to move those electrons. I'll write that down. Okay, so the fewer number of valence electrons that a material, an atom, has, the easier it is to subtract or to add an electron. Okay, so now I can go ahead and I can set up a little line graph over here. Number of valence electrons. I can start with 1. And I can go all the way up to 8. Okay, as it turns out, materials can have either 1 electron, 2 electrons, 3 electrons, 7 electrons, 8 electrons. They can have all numbers in between 1 to 8. And since the fewer numbers that the fewer number of valence electrons that an atom has, the easier it is to subtract an electron. So I can actually physically take this electron away from that atom, or I can give it an extra electron. Okay, so I would call this, if we have 1 valence electron, this is unstable. This is very unstable. And if we have the most number of electrons for valence electrons, then we have a very stable element. Now, if it's easy to take an electron or to give an electron, it means it's easier for these electrons to move inside of this material. So if you think of a copper wire, you have a lot of atoms that all have 1 valence electron that is very easy to move and to push from one atom to the next atom to the next one to the next one, etc., etc. So in other words, we have high mobility of valence electrons. High mobility. For that reason, we will refer to materials that have 1 valence electrons as being a good conductor. And since the opposite is true, if I have 8 valence electrons, I have a very stable atom, I have a very stable element, it is much harder to take an electron away or to give it an electron. So in other words, if I have 8 valence electrons for a material, I have something that is a poor conductor. In other words, I have an insulator. I have a good insulator. Okay, let's give some examples of this. Things that have 1 valence electron. Well, we already saw copper. What's the best conductor? What is the best conductor that's out there? Someone key it in. Somebody say it. Oh, looks like we got a fight between silver and gold, but the gold is winning. Gold. I got 3 for gold, 1 for silver. Who else wants to chime in? Do I have a 4th for gold? 4th for gold. Gold is not the best conductor. Silver is the best conductor. Okay, now here's my question to you guys. Why is gold so liked for connectors, for audio cables, especially those audiophiles out there? Oh, we got gold conductors over here. Well, it must be the best conductor because it's gold, right? Why do people like gold and not silver or copper? what does what does copper and silver do in air that gold does not? Yeah, rust. Okay, so gold does not oxidize. Gold does not tarnish like silver and copper does. Silver and copper, you put it in the presence of air, and all of a sudden it reacts with it, and it becomes not a very good connector. So gold is preferred for connections because of its ability to resist tarnishing and rusting, oxidizing, but truth be told, copper and silver are better conductors than gold is. Okay, so silver is the best, copper is a close second, gold is a close third. However, gold is preferred for connectors like audio connectors because it doesn't rust. Okay, so just a little side fun trivia over here. Okay, now the next thing to point to, this poor conductor, this insulator, this is stuff like glass, rubber, plastics, everything that you can safely shove into an electrical outlet and not zap yourself. Forks would definitely hurt you. Those are good conductors because they're made out of metals. But all of these are good insulators because they have 8 valence electrons. Now, let me go ahead and throw a wrench into this whole thing. All right. I am neither a good conductor nor am I a bad conductor. Therefore, I must be a Okay, I'll say it. Hey, there we go. I am neither a good conductor nor am I a poor conductor. Therefore, I must be a semiconductor. Now, we will talk about semiconductors. Semiconductors are the basis of all modern day circuits. So when you're talking about transistors and how you create, complicated circuits on silicon, like CPUs and digital circuits and all of that stuff, those are all semiconductors. And there's ways to cleverly manipulate this material, stuff like silicon and things like germanium, and we can modify them to be better conductors or to be worse conductors, and we can cleverly manipulate these to do some really amazing things. We will eventually get to that much later, but I just wanted to throw that in there for some fun right now as far as the semiconductor. Okay, so are there any questions about this right now? Okay, now let's talk a little bit about this outermost shell. I have the ability to give an electron or take an electron, especially when I have something that's got 1 valence electron, right? A good conductor. So let me go ahead and just draw something that's got 1 electron. Okay, so we got 1 proton, 1 neutron, and we have 1 electron. Hello, hydrogen. Now, I have the ability to take away an electron or to add an electron. When I do that, I change the balance of charge. Okay, so if I take away an electron, then all of a sudden I've changed the balance of charge, right? So over here I have one positive charge and I have one negative charge. We call this electrically balanced. Okay, but given that it's so easy to move these electrons around, and I'll give some examples in a little bit of how we can do that. But when I take away an electron, I'm left with something that is more positive. Okay, so we would call this a positive ion. Similarly, as taking away an electron, I can give something an electron. And if I give it an extra electron, I am now adding one extra negative charge to this atom, to this element, to this material. When I do that, I am left with a negative ion. We call it a negative ion. Now, this process of taking away an electron or giving it an electron is what's called ionization. Okay, so the process of adding or subtracting an electron to a given element is known as the process of ionization. Now, we care about this because we can go ahead and we can change the balance of materials. And by changing the balance of materials, we can create situations where it does work for us, or at least that it wants to do work for us. Now, we can go ahead and I will do an example where I do this ionization by using friction. So there are different ways to cause this to happen. We can do... We can cause this situation with chemical energy, or we can do it with static electricity. So in the case of something like a battery, that's chemical, that's chemistry. Now, if you look at a battery, like something like a AA, we know that there's a positive side and there's a negative side. Now, this positive side is created by having a material that has a lot of positive ions. Similarly, we have a side that's been created by having a lot of negative ions. We could also create this imbalance of charge by static electricity. And you've seen this before. Rub your feet on a carpet. You're going to start exchanging electrons with the carpet. And actually, I'm going to go through that example in a second. We could also create this imbalance with mechanical energy. Think of like a generator or an alternator like there is in your car. By spinning a magnet inside of a coil, you can actually create this imbalance. You can move the electrons. Now, for my example, we are going to create a charged body with static electricity. In other words, we're going to use friction. Now, let's go ahead and let's say that I have a balloon. And let's go ahead and say I got the professor's head. Okay, I know, I'm kind of balding, but let's just pretend that I got a good amount of hair. Well, actually, you probably can't tell on this camera. It's almost gone. Okay. Now, as these two bodies sit here, I got two separate bodies. One's a balloon, the other one's the instructor's head. And they are both balanced, meaning for every positive charge, there is a negative charge. And the same is true for the instructor's head. For every electron, I have an equivalent proton. I'm assuming that my head is balanced. I hope that's a safe assumption. However, if I start to rub the two together, I don't have any balloons on me right now, but if I rub the two together, so take the balloon and imagine I start shaking it against my hair, I am actually going to take electrons from my head and they are going to be deposited. They're quite literally, they're going to fly through the air and they're going to jump onto this balloon. So let's say I lost 2 electrons. Obviously, I would lose a lot more than that. But for the sake of not having to draw so many positives and minuses, let's just say I lost 2 electrons. Well, what did I just do? Well, again, the process of ionization. I lost a few electrons, they got deposited on the balloon, and my head lost 2 electrons, so now it's more positive. Now, if you try this at home with a balloon, you will find that after you shake the balloon or against your hair, you will find that the two will then stick to each other. Okay? So, in other words, the positive body and the negative body are now going to want to attract each other. We actually call this the basic law of charges. Okay, the basic law of charges say opposite charges will attract and like charges will repel. Okay, and so this is why when you take a balloon, you rub it against your hair, you actually have electrons that are jumping over into the balloon. Now the balloon has an excess number of electrons, making it more negative. My head has a lack of electrons, making it more positive. And now the two are just going to stick to each other. In other words, this balloon's just going to hang out stuck to my head because of static friction, because of this ionization that happens. Now, just to kind of bring this around full circle, because you're like, hey, this is an electronics class, but the instructor's talking about balloons and rubbing them on his head. Well, the same situation occurs inside of a battery. It's already provided for us, but we got one side that's more negative. One side that's more positive, and we have another side that is more negative. And if we use something like wire, something that has a high mobility of valence electrons, and we connect one side to the other, the basic law of charges tells us that these electrons are going to move around this circuit, right? Now, question, why don't the positives just move along that copper wire over to the other side? The protons are heavier. Any other suggestions?
The electrons are on the outer shell.
Yeah.
Able to move.
Yeah. The electrons can actually move. Think about what it means to be a proton. When you're a proton, you're hanging out in a nucleus. When you're hanging out in a nucleus, you are the material. So in order for the positive charge to move around this wire, would take something miraculous. This battery would actually have to physically move, right? But that's not what's occurring. What's occurring is the electrons are moving from one atom to the next. So if you think about your copper conductor, if you think about a wire, remember, a low number of valence electrons means that it's more easy to take away that valence electron or to give it an extra valence electron. So in other words, when I only have one valence electron hanging out, regardless of what the material is, the electron actually jumps from one atom to the next. You can almost think of like a bunch of marbles. So the marbles can move, but the pipe cannot. So you can think of the copper as being like a pipe. So what's happening in this situation, this is my pipe and marble analogy, is that the marbles are represented as the electrons are being represented as marbles. Those marbles can move, but the copper is the pipe. The nucleus is the pipe. And so the pipe can't actually move unless it was a liquid, right? So yeah, if I melted my copper wire down into a puddle, then yes, those positive charges could move around. But in a solid conductor, in a solid piece of wire, the nucleus is not free to move around. The electrons are. Okay, so if you look at something like plastic, where you cannot actually move those valence electrons, it's got no ability to conduct electricity. I can't move any of those electrons around. But if I got something like silver that's only got one valence electron, then it's super easy to pluck that electron and to push it along. And the way you cause that movement is by having this imbalance of charge that's kind of given to us in a battery. Does that kind of make sense? Just looking for a thumbs up from people or a yes in chat. I'll take anything. Perfect. Okay. If you got any questions, please, I'm going to pause here for a second. If you have any questions, please ask. Yes, I can explain that again. So in this battery, I have this imbalance of charge, right? I got a bunch of negative ions because whatever material this is has excess electrons. But over here, this side of the battery is made out of a material that has a lack of electrons. And so that lack of electrons gives us this positive side, this positive ionization. And now this is fixed into the battery. But if we give a transportation medium, something like a copper wire that has a low number of valence electrons, which means it is easy to take away or give an electron, then I've now given a path just like this, where one electron can jump to the other. So in other words, these electrons want to go to their home, and this is their home. They want to become balanced. Okay? The same reason that the balloon wants to stick to my head because of this basic law of charges. Because opposites attract. Well, the same is true over here. These opposites want to attract, and the only way the electrons can go home is by providing a wire or something that has a high mobility of valence electrons so that the valence electrons can all move back and forth. A dead battery is a balanced battery. Yes, I've never actually thought about it that way, but absolutely, yes. A spent or dead battery is a balanced battery. Okay? So hopefully that explanation kind of sets the stage. Now, what we're going to do eventually is we're not going to let these electrons go home for free. We're going to make them do some work for us. We're going to put something there. Maybe an electronic circuit, maybe a computer, maybe an LED. We're going to put something here, and we're going to be like, hey, electrons, we're not going to let you go home for free. You're going to do some work for us before. And in the process of doing that work, we're going to get something useful out of this. So this is the whole premise of creating a circuit. We create this situation where the electrons have to take this path and that they want to, and then we're going to put something in their way to make them not do it for free. They're going to have to do some work for us on the way home. Okay? So with that being said, I am done with the lecturing portion. I do want to do one lab experiment, and I got about 9 minutes left to do it. So I'm going to take the camera off. If you get motion sick, maybe move around a little bit or not look at the video. Oh, there was one thing I wanted to show first. Okay. Okay, I am going to show the most simplest of test equipment. This is the most simplest experiment involving moving electrons. And what it's going to consist of is a jar. And inside of that jar, we are going to have a conductor. At the bottom of this conductor, we're going to have two foil leaves. Two floating leaves that are still electrically connected to this conductor. But they have the ability to move and to pivot around. And this center conductor is isolated from its surroundings. So the only electrons that are going to be free to move are going to be inside of this conductor. Now, as this sits here, there is going to be one positive charge for every negative charge. Okay, so for every plus, I have a negative. And this would be electrically what? Balanced, right? Okay, so we're starting off with an electrically balanced system. We have one positive for every negative. Now, if I go ahead and take that balloon from earlier that I rubbed against my head, what happened to that balloon? Did it lose electrons or did it gain electrons? Yeah, it gained electrons, right? Some of the electrons from my head jumped over to the balloon because I rubbed the two together, and that friction energy caused those valence electrons from my head to jump over to the balloon. So now my balloon is more negative. So I'll draw a few extra minus signs in there. Now, here's the question. What is going to happen to these electrons if I bring the balloon close to this? I'm going to bring the balloon close to the top of this conductor. What do you think these negative electrons are going to do? The basic law of charges says they're going to do what? They're going to repel. They're going to move down. They're going to try and get away from that negative balloon, right? Opposites attract, like charges repel. Okay? So when I do that, The positives aren't going to be able to move. They're the nucleus. They're the substance of this material. They can't physically move. But the electrons, those valence electrons, they're free to move around. So the negatives are going to want to get away from this balloon. Now, they moved down. So now I have extra electrons hanging out in those two foil leaves at the bottom. Okay, now I changed the balance of those foil leaves at the bottom, right? What charge do the two foil leaves have?
Negative.
Yeah, they're both negative. So what are those going to do?
Repel.
Yeah, they're going to push away from each other. They're going to repel, not rappel, repel. Yeah, okay. So the two foil leaves are going to push each other away, right? Okay, now this contraption over here is referred to as an electroscope. And an electroscope is actually the first piece of electronic test gear, first piece of electronic test equipment that was ever developed for learning about this phenomena of electrons moving, of movement of charge. And I got one right here. Okay, so I'm going to go ahead and I'm going to move my web camera. Now put it on this tripod. And I'm going to come up with a way to make this light a little better. Okay, now this foil leaves that I was talking about, you can make one of these electroscopes at home. Just go ahead, look up on YouTube, and you'll see you can make it out of like foil paper and one piece of copper wire, and you can make it in a little mason jar. And I did that before, but I left that at school, and I had been wanting to buy one of these nicer ones for a while, so I bought it over the summer. Now, over here, you can see on this side, you can see a little hanging piece of metal. That's essentially our foil leaf. What you can't see is the top. Okay, that's a bit better. And the lighting is okay. That's actually the one drawback to my setup right now is I don't really have good lighting in this room. So that's something I'm going to be working on for the rest of the semester. But I need a balloon. I need something to charge. I got a plastic ruler. Let's just use this. And now I'm going to go ahead and, well, I'm running out of hair, so I got my own fur over here. So let's go ahead and use that. Now I'm going to rub the two together and actually see it on the other camera. And I want you to watch really carefully the foil leaf at the bottom, that little piece of metal. as I bring this charged body over to the top conductor. So what I'm doing right now is by rubbing these two together, I am stripping the electrons off of the fur. They are now depositing themselves into the outermost shell of the atoms on the ruler. And now I'm going to end up with a ruler that is more negative in charge. God, I hope this works. Huh? You guys see that? I'm not touching it. I'm just getting it close. As I bring the negatively charged ruler or piece of plastic over to the electroscope, it's causing the electrons that are in the whole balanced system to actually migrate down. And those foil leaves at the bottom are pushing each other away from each other. They're repelling each other. All right, can I get an ooh or an ah? Huh? 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 Yeah, right. Okay, awesome. Thank you. Okay, so that is my experiment. And I am officially 4 minutes over class. Okay, so I do apologize for kind of taking a little longer. It is a little slower with this online format. He's a wizard. Okay, so thank you so much for tuning in today. We will get into some more stuff on Thursday, and we will start talking about the labs. If you want, go ahead and download that zip file, and we will next lab be working with LT Spice. So at the very least, download that zip file from the website, put it on your computer so we don't have to wait for 10 minutes during lab next class. All right? And I will catch you guys later. Bye.
Bye, Professor.
See ya. I'll stick around for a few minutes if people like wanted to talk to me or whatnot.
Thank you, Professor.
Of course. Thank you. Take care.
I was on the other class.
Yeah, you needed to add, right?
Yeah.
Okay. Did you see earlier when I talked about adding this class?
Yeah, I sent you an email already.
Oh, you already sent it. Perfect. Okay, so I'll get around to that later today.
Okay. Anything else I need to do for that?
No, as long as you included the proof of the prerequisites and you gave me your name and your student ID, then that's everything that I need.
Okay. I accidentally sent you the wrong proof because I took Calc 3 already, so it wasn't showing my Calc 1, but I found it later on, so I sent you 2 emails.
Perfect. All right. I will look forward to that.
Have a good day.
You too. Take care.